Today we're going to be looking at summarizing quantitative data, generating the numerical measures of center and measures of spread of a distribution for a quantitative variable. And we're going to use them to summarize the distribution. So we're going to talk about measures of center, measures of spread, and a type of number summary that positionally summarizes our data and its visual counterpart called the box plot. So there are three characteristics of quantitative variables distribution. We can look at the shape, the center, and the spread. Now the shape, it's a visual. We can look at that through graphs. The center, the typical value, the expected value, that's a numerical summary. And spread, the dispersion, how spread apart our data is, also a numerical summary. Now the appropriate measure of center and spread depends upon the distribution's shape. Now, there will be a difference in analyzing populations versus samples. With a population, we know all the data. The descriptive measures of population are called parameters. Population parameters both begin with P, and parameters are often written using Greek letters, like the one seen here, which is mu. That's the mean, the symbol for the mean. For samples, we know only part of the entire data, in other words, subsets of the population. Those are descriptive measures of a sample, and they're going to be called statistics. Now, a sample, remember, is a subset of the population, so these are only estimates of the population. Statistics are often written using Roman letters. So our first look, measures of center. There are different measures of centers, but the ones we're going to focus on are the mean and the median. And in some of our distributions, we'll see that there is a mode, the data value that occurs most often. Now, the center of the data, these numerical values, they represent what we call the average, the typical value, the expected value of our particular quantitative variable. For measures of dispersion, that is, numeric values that represent the degree to which the values are spread out or spread apart. And there's different measures. We're going to look at the range, we're going to look at quartiles, but especially what's called the interquartile range, variance, and standard deviation. So let's look at one of our measures of center called the mean, the arithmetic mean. It is what we often do when we get the average, like our average in school. To compute it, you add up your data values and divide by how many you have. It's considered or can be thought of as the center of gravity. So if I had this data set, 1, 4, 5, and 10, I'd add them all up, divide by how many, and I would get the mean. Below you will see the R code for calculating the mean of this data set. Now we're going to look at a resistant measure of the data spread called the median. The first thing you have to do if you're going to try to determine the median is you must put your data values in order. So we have to arrange it in ascending order. And the median is at least half of the ordered data values are less than or equal to that median value. With ordered data, that is data arranged in ascending order, at least half of the ordered values are greater than or equal to the median value. So you can think of it either way. So it's the middle data value. There's as many to the right of it, data points, as to the left of it. Now, if n is odd, the median is the actual middle ordered data value. But if our n is even, the median is the average of the two middle ordered data values. If I want to find out the location of my median, here's the calculation for it. So L for location, M for median. The location of the median, you take how many are in your data set, add 1 to it. Take that number and divide it by 2. If we have an odd number, we're going to get an actual value. So in this particular example, if I had 25 in my data set, I'd take 25 plus 1, that's 26 divided by 2, it'd be 13. That tells me the location of my median after I have ordered my data set. So the 13th data value will be the value of the median. So let's look at some examples. So I have a data set 6, 2, and 4. If you said the median was 2 because it looked like it was in the middle, you're wrong, because the data set was not put in order. You'd have to go from 2, 4, 6. So that 4 would be your median data, would be the median value for your data. Let's look at example 2. Now I'm going to arrange it from smallest to larger, put it in ascending order. So it would be arranged 1, 2, 6, 11, and 11. Now we could use the location of our median. So that's 5 data values, add 1, that's 6, divide that by 2. It tells me that the third data value would be the median, and it is. So the location of my median is 3, meaning my third data value. So my median would be what that data value is. It's 6. Let's look at an even data set. So this one's in order for us already. So we have 8 data values. To find the location of my median, I'd say 8 plus 1, which is 9, divided by 2. I see that the location is 4.5. There's no index 4.5. So when I see the 4.5, it's telling me to use the data value for my data value x sub 4 and my data value for x sub 5, the one just greater than it. Add those two together, divide by 2, and that would be my median. So I would take those two middle data values, 77 plus 82, add them, divide by 2, and that's the median of this data set. Now, in a symmetric distribution, the mean equals the median, but if I have anything that's skewed, the mean will differ from the median. So in a picture, it's clear to see that the mean follows the skewness. So when left skewed, the mean will always be less than the median. And for the median, for symmetric, the median equals the mean equals the mode, the data value that occurs most often. And if I have right skewed data, my mean follows the skewness, so the mean will be greater than the median. And let's see how the median is a resistant measure of spread. As we can see, if I have this data set and I put it in order, I can see that the mean will be greatly affected. So if I have 6, 1, 2, the first thing you do is you put it in order. 1, 2, and 6. So my first data value equals 1, my second data value equals 2, and my third data value equals 6. The location of the median, like we said, we have a sample size of 3. So the location would be 3 plus 1, the sample size plus 1 over 2, or my second data value is my median. So in this case, the median is 2. But let's say I had a recording error, and I recorded 6 as, let's say, 600. I put an extra 0, or an extra 20 in this case. I put my data value in order. My median doesn't change. My median is still going to be 2. But let's see what happens with the mean. If I calculated the mean here, I add up my data values, 6 plus 1 plus 2. I'd get 4.5. But let's calculate the mean for this and see how greatly affected my mean value is. This would be 603 divided by 3. Look how different. Oh, and this would be divided by 3, sorry. This should be, because my sample size is 3, I add up and divide by how many I have. So my answer here would be 3. And this one, if I do this, this is 603, my mean changes. Look how greatly it was affected. And look what's happening here. We're really skewed right. We'd have 1, 2, and then all the way to 600. This thing would certainly be skewed right, or have that outlier to the right. And it really pulls the mean toward it. So the mean is greatly affected where the median didn't get changed at all. So when data has extreme values, outliers, or heavily skewed data, that is unusually large or small values if we have outliers, or it's skewed, the median is preferred to the mean because it is more representative of the typical value of the variable. So our central tendency, the two that we're going to focus on is the mean and the median. The mean is that center of gravity. We add all our data values, divide by how many we have. It's useful for roughly symmetric quantitative data with no extreme values. The median splits the data in half, so you have as many data points to the right as to the left, whereas the mean, it's the values. You have as much value to the right of the mean as to the left. The median is the actual data points. It's useful for highly skewed quantitative data or data that has outliers or extreme values. Now it's time to go into a look at variability, that spread of your data. So the measure of center alone can be a little misleading. A useful numerical description of a distribution requires both the measure of center and the measure of spread. And these are the measures of spread we'll be looking at. The range, using the first and third quartile to get the interquartile range, the variance and standard deviation. So we're first going to look at the range. So the range, the maximum data value minus the minimum data value. So if I had a data set 6, 1, 2, 6, 11, 7, 3, and 3. The first thing I'd do is I'd put it in order. 1, 2. Now you keep all the data values. If 3 is twice, we need to see it twice. So then we have 6, 6, 7, and 11. So I have my data value 1 is 1. Data value 2 is 2. Data value 3 is 3. Data value 4 is 3. Data value 5 is 6. Data value 6 is 6. Data value 7 is 7. And data value 8 is 11. We put it in order and we all know exactly which data value equals what. Now, to find the range, I take the minimum data value, the smallest data value, which is 1, and I'm going to subtract it from 11. So 11 minus 1. So my range is 10. So you want your max data value minus your minimum data value. So my range is 10. Now the range isn't resistant, because what would happen if I had have done 11 wrong and put 110? Okay, so mistakenly I added a 0. I would calculate my range as 110 minus 1, or 109. That would be very different. So the range is not resistant. So now we're going to look at another measure of spread called the IQR, the interquartile range. The interquartile range is your third quartile, Q3, third quartile minus your first quartile. But then you could say, well, what's a quartile? A quartile is the position, that data value such that, and in Q1, my first quartile, or Q1, 25% of the data values, data points, are below it. Otherwise, we could say that this is the 25th percentile, because that's exactly what a percentile is. 25% of the data values are below it. Q2, or my second quartile, we already know this one. 50% of the data points are below. We know that as our median, otherwise known as the 50th percentile also. So it gets an extra name. It's awful special. And then Q3, our third quartile. And I think now you could kind of guess, looking at these, this is what we call the 75th percentile. So 75% of our data points are below, in other words, the 75th percentile. So Q1, 25% of our data points below, so it's our 25th percentile. Q2, our second quartile, 50% of our data points are below it. It's the median, also known as the 50th percentile. And Q3, the third quartile. That is 75% of our data points are below it. That's our 75th percentile. And if you kind of look, if we had really nice data, it would look something like this. So here's all our data. And here's Q1, here's our min, Q2, Q3, here's our max. And like I said, this is really nice data values. This right here would be 25% of my data points are below it. Q2, or the median, 50% of the data values are below it. And my Q3, 75% of my data values are below it. So there's 25% of my data between Q1 and Q2, 25% of my data in between Q2 and Q3, and then here's the upper 25th percent, or 25% of my data between Q3 and my maximum data value. 25% of my data points are to the right of Q3. So the interquartile range, Q3 minus Q1, is the middle, meaty 50% of my data. It's that range of data, the actual data values, you subtract those two, and that's going to be the length of my middle 50% of my data. And look what happens. It would lop off most of our skewness and any outliers that would be on the right or left. So the IQR is a resistant measure of spread. So you'd have to find Q3 and Q1, subtract the two to get your interquartile range. Now there's many different ways in a data set, believe it or not, to calculate Q1 and Q3. So what we're going to do is we're going to use the output of RStudio to calculate the IQR and then to use it. So looking at this output in RStudio, calculate what the IQR is. Well, reading off the output in RStudio, we see that Q1 is 10.5 and Q3 is 22. So the IQR is going to be 22 minus 10.5. So we would say the IQR is 11.5. Now we could just use R to get that output. If we used code, we could actually get the IQR, but we can also calculate it ourselves. And so just so that you know, on our tests, I will give you this output and you're going to have to calculate IQR. So now it's time to look at the 5-number summary and what it is. The 5-number summary is your minimum data value, the smallest data value, your first quartile, or that 25th percentile, your median, or your second quartile, or that 50th percentile, your third quartile, or the 75th percentile, and your largest value. That would be your 5-number summary. When we use the summary command in RStudio, we're going to get too much information, only by one thing. We're going to get the mean. The mean is not part of your 5-number summary. So if you were to write your 5-number summary, you would say it's 5, 10.5, 18, 22, and 27. The mean is not part of our 5-number summary. This leads us to the box plot. It's a graphical representation of the 5-number summary. Lines will extend from the box for you to see the minimum and max. These lines are sometimes called whiskers, so people call this, instead of just a box plot, they'll say it's a box in whiskers. This is what it looks like. The box represents that interquartile range from Q1 to Q3, and it will show a line where the median is, and the whiskers extend to your max and your min. To note, when using R, the whiskers show the minimum and maximum values within what is called the lower and upper fences. The number greater than the upper fence or smaller than the lower fence would be considered outliers, and you would see asterisks to indicate these outliers. We'll talk about that a little later, but just to let you know. Outliers, extreme values in our data, extreme observations that would be in our data. They can occur by chance occurrences, measurement errors, data entry errors, or sampling errors. Sometimes outliers are not necessarily invalid data, and that would create issues for us, and it makes our analysis a little more complicated. So if we have outliers that are valid data, they're part of the system, we cannot just throw them out as if they were just a measurement error or a data entry error. We actually have to deal with them in our analysis. So we always have to investigate outliers. So I talked about this upper and lower fence. Those data values, such that anything lower than the lower fence we're going to consider an outlier, and anything greater than the upper fence will be considered an outlier. We have a calculation that can help us to determine if there are possible outliers. So we can get the range of data our value should be if there are no outliers. So in our data, we can use the calculation to actually get a value we call the lower fence and a value called the upper fence. And if our data lies within the lower and upper fence, all data values are between those two values. There are no outliers in our data. If we create a lower and upper fence and we have some data values out here or data values out here, so if there's any data, even just one, we would have outliers. So any data value greater than the upper fence would be an outlier, and any data value lower than the lower fence would be an outlier. So again, any data values greater than our upper fence value would be considered an outlier. Anything smaller than our lower fence would be considered an outlier. So let's look at a situation, or let's look at this and what's going on. So if I have a box plot, here's Q1, Q2, and Q3. Here's my upper fence and my lower fence. How do we get that? The lower fence is taking Q1 and subtracting from it this distance times 1.5. So 1.5 times that distance. So that distance is 2. 1.5 times that would be 3. So I'm going to subtract 3 off. There's where I get my lower fence. You take that same 1.5 times 8, whatever this length is, to get the upper fence. Now remember, this is the middle meaty 50% of my data. 50% of my data. We would expect the other quartile to be somewhere around in here, really. But look how far that's out. So we're saying any data value larger than that upper fence or smaller than that lower fence, that's far away from most of our data. And we'll consider that as an indication that those values are outliers. So that's how that works. And this is a calculation that we would use. So once again, it's time for you to work. Given this RStudio output, calculate the lower and the upper fence. And when you do that, you got that the lower fence was negative 6.75 and the upper fence was 37.27. Now we know our minimum data value is 5. It would land inside of here, but the maximum data value is 27. It lies within here. So we're going to look at this, that on a number line, my lower fence was calculated to be negative 6.75, and my upper fence was 39.25. And I had that 5-number summary of 5, 10.5, 18, 22, and 27. So that means we have a range of data. We said our data value should be in between negative 6.75 and 39.25. Lower fence, upper fence. We calculated that. My minimum data value is 5. 5 definitely is within this range. So we know there's no outliers to the left of our lower fence. And then our maximum data value was 27 because it gave it to us as in our 5-number summary. And 27 is within here. So based on our data and getting the lower and upper fence, there are no indications that there are outliers. So our data set looks like there is no outliers. Now let's just look at a case if I have the 5-number summary, but I'm looking at the min and the max, and I've calculated the lower and upper fence. And I find out that my data should be between 3 and 30. When I look at 12, 12 is within here, so there's no outliers to the left. But when I look at this, my highest data value should have been 30. We know we can only state there's probably at least one outlier, the maximum data value, because it lies outside of there. There could be more. We'd have to actually look at the original data set. But based on the lower and upper fence in our 5-number summary, looking at the min and max and calculating that lower and upper fence, we see that there's at least one outlier in this case. Now looking at the previous data set where we said there are no outliers, when we actually use R to generate the box plot, we see the box plot. And if we don't see asterisks, then we know that our data value, that there are no outliers in here, and that these are the values for the min and the max. Now we're going to look at summarizing quantitative data when we look at variability through variance and standard deviation. So for measures of spread or dispersion, we've looked at the range, the IQR. We use the IQR to see if we had any outliers. But now we're going to look at another measure of spread, the standard deviation. That is the average distance each data value is from the mean. So that makes sense. Getting the spread, the average distance each data value is from the mean. If it's small, then that means there's very little deviation of our data. That is, they're really close to the mean. But if my average distance is large, well, then that means my spread is large. So let's see how that would work. So let's have a data set. So we're going to take a look at this data set. And first we're going to calculate the mean. And we're going to say this is the population. So when we use population, our sample size is denoted by a capital N, and we have 1, 2, 3, 4, 5 in our population. So to calculate the mean, it's going to have that symbol mu, lowercase m in the Greek alphabet, and we're going to sum up all our data values from I equal 1, 2, 3, 4, 5 to 5, and then we divide by how many we have. So that's capital N I should put there, and capital N there. So we're going to sum up x1 plus x2 plus x3 plus x4 plus x5 and divide it by 5. And we know the values of these. 2 plus 3 plus 5 plus 17 plus 23 divided by 5. So I just add them all. I get 50. Divide that by 5. My mean is 10.0. Now that I have that, I now can look at this average distance each data value is from the mean. So I'm going to say 2 minus my mean, which is 10, plus 3 minus 10, plus 5 minus 10, plus 17 minus 10, plus 23 minus 10. And the average, and these are all distances, and the average distance divided by, so we have 5 of them, we divide it by 5. But when we do this, we say, okay, well, that's minus 8, that's a negative 7, that's a minus 5, 17 minus 10 is a plus 7, and then plus 23 minus 10 is 13. Divide that by 5. But look what happens when I add this, I get 0. And I'm going, but there's definitely variation. They're not all the same number. Variation just means they're different numbers. But it will always turn out to be 0 because by the definition of mean, there's as many arithmetically, as much quantity above the mean as below the mean. So this would always happen. So we can't get straight away to the average distance each data value is from the mean. We have to do something called variance. And that's where variance is important. We need to get variance before standard deviation. So variance is, by definition, 3 bars is how I write a definition, is the average squared distance each data value is from the mean. So I'm going to square all of these. So that would be 8 being negative 8 being squared, negative 7 being squared, plus negative 5 being squared, plus 7 being squared, plus 13 being squared. And now this is going to give me a whole different answer when I do this. It's going to give me 356. 64 plus 49 plus 25 plus 49 plus 13. And then I have to divide that by 5. So this is what we call variance, the average squared distance. And variance is represented by sigma squared. Like a weird looking O squared. This is lowercase s in the Greek alphabet. And it's being squared because it's our standard deviation being squared. So this is sigma squared. So in order to get standard deviation, sigma, I just take the square root of variance. And this is population standard deviation. Population variance that we're looking at right now, and population standard deviation because we're in a population. And what we're going to find out is that the actual calculation of population standard deviation and sample standard deviation, they're actually different. So when I get this, I get 8.4 as my population standard deviation. Now, when we calculated the mean, so I just want to show you, we got population mean. Look what happens when we do a sample. The sample mean is represented by X bar, and it's the sum from I equal 1 to a sample size divided by that sample size. The actual way that we do it doesn't change at all. So if I had, let's do another sample and calculate the sample mean. So if I had the sample mean and my sample now looked identical, so the sample was 2, 3, 5, 17, 13. Let's say this was in inches. Somehow this new thing was in meters, but they had the same data values. Okay, this is weird, I know, but it had a sample size of 5. When I calculated the mean, I'd end up with the same, 2 plus 3 plus 5 plus 17 plus 13 divided by 5. I'd get the same sample mean of 10. But what happens now when we do variance is very different. So variance will be S squared, because sample variance would have a Roman letter representation called S for sample variance, which would be sample standard deviation squared. We'd have 2 minus, and now this is a sample mean. So let's even take a look at, if I put this represented in letters in the way we would represent it, this right here, our variance, let's do it here, would look like this. The summation of each of our actual data values minus the population mean squared divided by n, and sigma would be the square root of that. Our sample variance has a very different formula, because when we do this, we'd have xi, but all we have is the sample mean, and we're squaring that error. That's not good. When we do that, we are creating even more error in there. And as we know, if we divide by a smaller number, we actually get a larger number. So what do I mean by that? If you had 12 divided by 6, we get 2. But every time I make that number smaller, this number gets larger. So when we divide by a smaller number, we get a larger number. So we want to hedge our bets because we're making an error here. So we're going to divide by a smaller number. And that smaller number is our sample size minus 1. And you're going, okay, magic math. So why sample size minus 1? Well, there's other reasons beside this idea that we're creating more variance, so let's make a bigger number. This is called the degree of freedom. The degree of freedom is your sample size minus how many parameters you are estimating. So in this, our degree of freedom, we're taking only one parameter and estimating it by a sample mean. So we take our sample size minus 1. So we divide by our sample size minus 1, that degree of freedom. So for every parameter you estimate, you take another one away from the sample size. So if I was estimating 2 different parameters, I'd say n minus 2. But in this case, we're only doing 1. So our actual way that we calculate standard deviation will now change based on this. We're going to divide by n minus 1. So when we work on this, instead of 356 divided by 5, we're going to have 356 divided by 4. And when we get that, we get a little bit of a different number. I'm going to get 89. So my variance is 89. My standard deviation will be the square root of 89 to give me 9.4. A little bit larger, as we would have expected and should have expected, since we're estimating our sample mean. So how do we know our best measure of center and spread? Well, if we have any data that is not symmetric, we're going to use the median and interquartile range. So only for symmetric data will we use the mean and standard deviation. So this is left skewed data. What's the best measure of center and spread? You're right, the median and the IQR. So center, spread. For right skewed data, asymmetric data, the best measure of center and spread. Correct, median and interquartile range. For symmetric data, this is when we use for center, we would use the mean, and for the spread, the standard deviation. And this one, what would we use for this one? So we have symmetric data, but there's outlier or outliers. So we would use for center, the median, and for spread, the IQR. So whenever there's outliers, we want to use the median and interquartile range. For asymmetric data, median and interquartile range. Symmetric data, the mean and standard deviation. Well, thanks for watching, summarizing our quantitative data. Thanks.